Assalamu alaikum, I am Osama Alim Shami, and today I welcome you all to APAN58 conference. Today I am presenting my paper Deciphering Crop Dynamics, Leveraging Field Geometry for Precise Image Registration and Enhanced Insights. So here are the authors. Since time is short, so I'll move along, and in case you have any questions, you can ask in the end. So here's a brief outline of my presentation, which includes introduction, motivation, methodology, followed by results, conclusion, and question answers. So starting off, what are unmanned aerial vehicles? Well, unmanned aerial systems are air vehicles associated and associated equipment that do not carry a human operator, but instead are remotely piloted or fly autonomously. And they are commonly known as unmanned aerial vehicles, remote piloted aircraft systems, and drones. And they are usually consist of an aircraft with no pilot on board, a remote pilot station to control that, a command and control link, and a payload specific to the intended application and operation. So in agriculture, unmanned aerial systems are utilized to capture time series data to provide farmers and plant breeders with an unparalleled view of crop health, growth patterns, and environmental conditions. Hence, it paves way for precision agriculture, promoting efficiency, maximizing yield, and fostering sustainable practices. In precision agriculture and high throughput plant phenotyping, accurate analysis of time series remote sensing imagery depends on precise spatiotemporal registration, which basically involves two things: aligning spatial data to ensure consistent representation of geographical locations across images over time, and synchronizing image acquisition timestamps for valid comparisons. Well, inaccurate registration results in misalignment, which can lead to certain issues like incorrect yield predictions, unreliable phenotyping data, etc. Global navigation satellite systems are normally used, but they are incorrect for geospatial alignment. But they can be improved by employing precise methods like RTK GNSS receivers and ground control points. However, both of these methods have some issues or drawbacks. Like the first one is expensive and complex to manage, while the other one is also challenging to physical install and maintain it. And to avoid these, feature-based methods are commonly employed for accurate image registration, such as SIFT, BRISC, and SURF are used for certain tasks. However, when applied to agricultural fields, the existing feature-based methods result in pronounced visual alterations due to various factors like crop growth, soil moisture variations, and movement of agricultural machinery. And hence these established techniques fail to find reliable matches, especially in case of crop breeding trials having homogeneous small plots due to intricate changes over time. Here you can see the results that they cannot find relevant matches when evaluated over time. So the problem here is the existing unmanned aerial system image registration techniques cannot be incorporated in agricultural landscapes due to their high cost, demanding requirements, or due to their poor performance, leading to inaccurate results. And the solution is to solve this image registration problem by proposing a robust technique which is not only cost effective but also yield accurate results when employed on agricultural landscape. So starting off with the proposed methodology, we propose a UAV imagery methodology comprising of 6 steps, which are image acquisition, processing, feature extraction, description matching, and transformation and reprojection. Here is the brief workflow, which I'll be looking forward in the upcoming slides and discussing them as well. So our experimental setup is basically in National Agricultural Research Center with which we collaborated with, and there were certain wheat fields of 215 wheat fields basically of the dimensions 1.5 meters into 2.5 meters of various wheat cultivars arranged in a checkerboard layout. And the duration was 1 month in which we acquired the drone imagery. And we assumed certain assumptions for our experiment, like the field comprises of numerous small plots and as in common breeding trials, and also we placed static plots and centroids and in those plots. So for image acquisition, basically we used a DJI Inspire 2 drone with a Centera double 4K multispectral sensor whose specifications are like it can capture high resolution RGB imagery, and the image capturing span was from February 23rd to March 23rd, and we did 5 surveys 1 week apart, and the drone was basically at an altitude of 3.35 meters, and it gave us 1.2 centimeter per pixel ground sampling distance. So the first step was image pre-processing, which involves the use of Pix4D Mapper, which is a professional software for photogrammetry. And it comprised of 3 steps: automatic image alignment, ortho rectification, and mosaicing. And ultimately, we acquired a high quality ortho mosaic of the same field. Coming on to the second step, basically it is feature extraction, which involves segmentation, refinement, and centroid calculation. So for segmentation, we use the segment geospatial package to acquire segmentation mask as polygons, and for refinement, we basically eliminated polygons with high defined areas on statistical thresholds or rules. And for centroid calculation, we again computed centroids on the on the remaining polygons to define them as feature points. The next step is feature description, which basically involved encoding the local geometry surrounding each centroid into a descriptor vector for robust image matching. So basically, after this step, we acquired a feature descriptor which was which basically was invariant to translation, scale, and rotation. The next step was feature matching, which basically involves establishing correspondences between the feature descriptors extracted from the reference image and the sensed image from the drone. And it also uses a 3-stage pairwise matching approach. First one is basically filtering based on dimensional compatibility, which used feature descriptors from both the reference image and the sensed image, and it discarded incompatible matches. Second one was filtering based on pairwise distances via L2 norm. So it also involved eliminating further, you can say, the candidate matches which weren't of our use, and it utilized the L2 distance. Last one was outlier mitigation based on analysis of histograms and of distances and angles, where basically we again computed histograms of the matched pairs to retain the pairs while residing within peak regions of these histograms. For estimating transformation parameters and image resampling, we utilized affine transformations, and this is the equation which we used. And basically the solution of these equations resulted in a transformation matrix that encapsulates the geometric relationship between reference image and the sense image. So coming on to the results, this is the validation strategy which we used. We basically employed 4 ground control points evenly, and then corresponding centroids were determined within both the reference image and the sensed image to represent these points. Then the geographical distances were computed within respective centroids in the reference image and the registered image to quantify geometric accuracy. And then the root mean square error was used as a metric to mitigate the impact of potential outliers in the distance measurements. Here are some of the results. Like you can see the reference date and reference image date and the sensed image date, and there are initial matches, the inlier points, and the corresponding root mean squared error for each trial. So I'll come back to this if you want. Like there are 3 different examples from the previous table. There's a trial 3, trial 4, and trial 6, and these are the examples of the images which we acquired and pre-processed after acquiring from the drone and computing an orthomosaic and all these steps. So here are some observations from these results. There's a slight we observed that there's a slight correlation between temporal proximity and feature matching efficacy. For example, orthomosaics closer in time yielded a higher number of matched features. Secondly, the registration sessions that we concluded approximately 1 week apart exhibit both an increase in matched features and inliers, ultimately contributing to a lower root mean squared error. So spatial distribution of match points within the field significantly impact registration accuracy. For example, a wider distribution of these match points result in lower RMSE values. So let's look at the examples of the trials which I showed earlier. Trial 6 had 4 inliers which achieved a minimal RMSE of 3.71 centimeters due to wider dispersion of these points. Similarly, trial 3 had 9 inliers, but it demonstrated a higher RMSE of 10.15 centimeter due to their concentrated positioning within the field. Sorry. And last one was trial 4, which processed 128 inliers, achieving the lowest RMSE of 2.68 centimeters due to its robust combination, which signifies the importance of both matched feature quantity and distribution in optimizing registration accuracy. So concluding the results, well, despite exceeding the 1.2 centimeter pixel level resolution, which was acquired by our drone and sensor, the observed root mean square range of 2.68 centimeter to 10.15 centimeter remains acceptable considering the meter scale dimensions of the plot. And this performance gap compared to the expensive 1 centimeter accurate RTK GNSS receiver is still relatively modest. And these results show the potential of our proposed methodology for effective registration, temporally separated and spatially misaligned UAS based imagery. So concluding my presentation, well, we basically provided accurate tracking of temporal and spatial changes in agricultural landscape, since it relies on precise UAS image registration. And existing methods like RTK, GNSS sensors and GCPs provide high accuracy, but they are often costly and logistically demanding. And we proposed a cost-effective feature engineering-based solution for robust UAS image registration, which leverages the inherent geometry of the fields to create a resilient descriptor which is resistant to common geometric and photometric transformations. And our approach ensures acceptable registration accuracy and offers significant cost and logistical benefits, hence enabling efficient and affordable monitoring of crop health and growth and other parameters. And for future work, since we use the wheat you can say crop, and the fields were in checkerboard effect, we can use the same strategy for other arrangements such as grid and strip row layouts. So these are the references, and that's all from my side. If you have any questions, you may ask. Thank you.
Thank you very much. We have also online participants. We welcome them all. And now we have the question answer session for the first presentation. So anyone, if they have any question from the audience, from the online participants, they are welcome.
Yes, please.
First of all, I would like to congratulate you on this nice piece of work. Well, I am actually a plant breeder, and I have seen from your presentation that you have taken images and processed them. My question to you is that is it possible now, after your work, to go further and to give the detailed attributes, the phenotypes, particularly, for example, if you talk about wheat, like what is the size of the wheat spike, how many grains are in there, or growth, or these different kind of phenotypic attributes,
right.
and how far or how long will it take to image them and to detect precisely, so that we can differentiate between all our breeding lines to select which one is the best one according to our objective. So how far are we have to?
Since I told earlier, this project is in collaboration with National Agriculture Research Center. So obviously they provide us the phenotypes of all the breeds, and they have their data as well. So in case you are interested, you can connect after presentation, and we can discuss with them as well in case you want certain information regarding the plots. And obviously, like the current plots, we set up our drone height accordingly to acquire precise imagery. So based on that height and other factors, we obviously decide these factors as well, like on what height the drone shall fly and what sensors shall we use. And our lab is also working in, you can say, phenology estimation, like over time how the crop grows, and we are detecting stages as well. So there are applications obviously in various domains, but you have to specify like in which domain you want to target, and what features are you basically extracting. So in case you have any particular concerns, you can feel free to ask and connect further.
Thank you very much. I'm Professor Dr. Amjad Khan. My one question just for understanding.
Yes, sir.
What is the role of temporal and spatials, the term you use in agriculture
All right.
technologies? Thank you.
So basically temporal and spatial, you can say resolutions or the terms are utilized in sentinel, in satellite or drone based imageries. Like spatial resolution is basically the resolution of the image you are capturing. Like you can say there are different satellites, but not every satellite can precisely or clearly capture a same image. Like even if you see the Google map, once you are zooming into a certain image, there are different satellite names being changed. So every satellite or sensor have a particular resolution, like we have the resolutions in cameras. So we have to define that spatial resolution as well, or we have to look for that spatial resolution. Similarly for temporal, like since it is a crop related task, so you know that with time the crop grows, and we have to capture all those timestamps as well. So that's the main thing, like we use temporal and spatial alignment. Like with time, even the plot boundaries are the same, and we don't capture any other areas, etc. So we have aligned the spatial as well as temporal context both. Thank you. Any other question?
I would like to just highlight how generalized is this framework.
Sir, well, we can obviously, since it was particularly for the wheat crop, I think we can also apply this on other crops based on again the plot sizes and the provided data. NARC has specified fields for them for experimental and other purposes. So it depends, like if there is any other data provided, and also there are any, as I said, it can be used in different layouts as well. Like our plot was in checkerboard layout. We can also try to accommodate this in row and strip layouts where the arrangement of the plots is different compared to this. So it can be applied to those as well. Since we are registering the images based on computing orthomosaics and then computing the centroids, or you can say distances, to align them.
Thank you very much.
Thanks
Any
so much.
question from the online participants? Okay, we can move to the next presentation. Thank you very much for the
Thank you.
presentation. Next presentation is, the title of the paper is Sportifying the Sentinel-2 Imagery, Harnessing the Power of Attention in Real-World Single Image Super Resolution. And the author is going to be Salman Akhtar.
Shall I start?
Please start.
So this is my another paper which got accepted. So it's basically about improving the resolution of the satellite imagery. So it's titled Spotifying the Sentinel-2 Imagery, Harnessing the Power of Attention Networks in Real-World Single Image Super Resolution. So here are the authors for this, and again the outline is introduction followed by methodology and experiments, results and discussions, conclusion and references. So here what is remote sensing? That's the first question which normally arises. It refers to the process of acquiring information about any object, area or phenomenon without any physical contact. So it involves the use of various sensors and instruments like satellites, aircraft, drones and ground-based devices. In remote sensing particularly, satellite imagery has played a vital role in various applications like environmental monitoring, agricultural crop type identification, urban planning, etc. So the question arises, why there is a need for satellite imagery enhancement? Well, as I told earlier, there is always a trade-off between different resolutions like spectral, spatial, temporal resolution, and it means that no specific sensor provides an overall optimal resolution. So we have a trade-off between the mentioned resolutions. And here are some of the factors which lead to poor quality remote sensing images with blurred regions. Like there's a limitation in the current remote sensing imaging technology. Again, there is the high cost to upgrade the sensors present in the satellites or drones, and there is an influence of external environment like clouds, any other environmental conditions as well. So satellite imagery enhancement is necessary to acquire a detailed and accurate visualization of Earth features, which is easily interpretable. So there are two basic techniques or major techniques which are used for resolution enhancement. First one being the pan sharpening, which involves the fusion of low resolution multispectral image with a high resolution panchromatic image. Second one is super resolution, which involves the enhancement of spatial resolution of a single image, which is termed as single image super resolution, or a sequence of image, which is termed as multi-image super resolution, using high resolution image as the ground truth. So here are some of the state-of-the-art single-image super-resolution models. But although there are various models which have been proposed, like there are CNN-based, GAN-based, and transformer-based models, but in most of the cases you can see that training being done is not on the real-world data. Like they have to downsample the high-resolution image to acquire the low-resolution image, and then train the same model on the same low-resolution image, and then train the same models on that low resolution image to by keeping the high resolution image as the ground truth. And you can see from the table the common scale factors are 2 times, 3 times, 4 times. Only one paper utilized 8 times scale factor. So even the benchmark datasets used mostly are comprising of natural images like div2k, etc. And even the datasets which I mentioned in the table, which involve satellite imagery, are either not temporally matched or geographically matched. So again, it means that the low resolution image is missing, and it needs to be generated from the high resolution image. There was some dataset recently published that is sent to WenMu-S. It has a Sentinel-2 as a low resolution satellite with a spatial resolution of 10 meter per pixel, and a WenMu-S as a high resolution satellite with a spatial resolution of 5 meter per pixel. But the resolution ratio is too big, so it means that it can only be used to upscale the image 2 times only. So the drawbacks were the dataset availability issue for Pakistan, and also the resolution ratio offered was quite low. Another dataset is WorldShred data, which covered 10,000 square kilometers of area, and it has total around 400 images. It also utilized a Sentinel-2 satellite as a low resolution satellite with maximum spatial resolution of 10 meter per pixel. But the high resolution satellite here is Spot 67, which offers a maximum spatial resolution of 1.5 meters per pixel. So the resolution ratio offered is around approximately 6, you can say. And the benefits are that like Spot 67 and Sentinel-2 both offer data for Pakistan, and the resolution ratio is also good, which is offered. And but there are some drawbacks in this data, like there are some contrast issues if you compare the lower resolution and the high resolution image. And the original authors of this paper targeted a scale factor of only 3. So the problem here is the existing single image super resolution models are trained on datasets having pseudo LRHR image pairs, and they usually learn the inversion of degradation process, are not robust to image variations, and cannot handle large upscaling factors effectively. And the solution statement here is to solve this SISR problem as a domain translation task after incorporating changes in the SISR model either in the network side or loss function, and training it on a real world remote sensing data so it can model the real world remote sensing images, remote sensing single image super resolution better, is more robust to image variations, and can handle significant upscaling factors effectively. So here are the main contributions. Basically, we proposed a data preprocessing pipeline to enhance the visibility of the WorldShred data, as I told that it had some issues. And then we proposed the RWSR GAN, which targets a custom scale factor of 6 and handles the real world SISR problem effectively. So here you can see these are the stats which I discussed earlier as well. But the important thing is like this is the Sentinel-2 Spot 67 bands, and you can see the highest spatial resolution offered is 1.5 meters per pixel. For Sentinel, we are using the RGB imagery, so they offer 10 meter per pixel spatial resolution. And corresponding to each high resolution image, this data has 16 low resolution images, which are temporally as well as geographically matched. So here are some of the you can see data set. Like the first one is the low resolution image from the Sentinel-2, second one is the high resolution image from Spot 67, and the third one is high resolution image after pan sharpening it using their own data to 1.5 meters per pixel. But you can see the images are a bit dark, so these are the issues which were which I was discussing earlier. Here are some of the issues. Like you can see, there are cloudy instances. Then some of the images have these cropped black regions where data wasn't acquired properly. Some have these overlays, and then there are washed out images, dark images, and there are some color mismatches, etc. So here is the proposed data pre-processing pipeline where we are taking low resolution and high resolution images. And this is the high resolution image at 1.5 meter per pixel. Then we are applying some image processing techniques, which I will be discussing in the next slide. And after stage 1 pre-processing, you can see the image is a bit improved, but it still is a bit faded out. So we then again performed another step to acquire it in a better acquire better results visually. So there are 4 steps in our pipeline. The initial preparation, which comprise acquisition of this data and computing these LR and HR images from the multispectral images of Sentinel-2 and Spot 6-7, and then preparation of high resolution image by pan sharpening the high resolution image using the panchromatic band provided in the same Spot 6-7 image. Stage 1 pre-processing involves histogram matches on HR and HR dash images, followed by gamma correction of gamma is equal to 0.7 and adaptive histogram equalization based on mean pixel intensity value after setting a mean threshold of 0.15 to enhance the brightness of those dark images. And since I told that after this first step some of the images were still faded out, so we performed the same step on those images. But now we took the histogram, after histogram matching, we took gamma value of 0.2 and then adaptive histogram equalization again to enhance these washed out images. And lastly, the clouds, cropped area images or overlay instances were removed manually, and we filtered out those so they won't affect our training. And we also manually inspected some LR images, like there were a few flawed images, so we replaced by their other counterparts since there were 16 images of the same instance being provided by the dataset authors. So coming on to the architecture of basically our real world super resolution GAN, it uses a generator of activated residual and residual dense network, which has a feature extraction part and upsampling and feature refinement decoder part, which acts as a decoder. And the discriminator used here is VGG style CNN based, which performs feature extraction and then scalar value prediction. And the loss function used here is L1 plus is a combination loss, which is a combination of L1 loss, perceptual loss, adversarial loss, and patch loss. So here are the experimental settings. We, as I told, we targeted a scale factor of 6. The input low resolution and high resolution images are scaled to 960 cross 960, and the data set split is like 80-20-20 ratio. And these are some of the hyperparameter settings in the table which I used for my methodology. Here is the diagram. Like you can see that this is the generator where the low resolution image is being passed to the encoder and then to the decoder. Here the main thing is this yellow block, that is ARRDB, which accumulates to ARRDB net. So the activated residual and residual dense block basically comprise of these attention enhanced residual dense blocks, like 3 in series, and then after some scaling the skip connection is being added to form the output. And it involves this modified attention module, which I'll be discussing in the next slide. So modified attention module can be either spatial attention block, channel attention block, or modified channel attention block, or any combination of these, or one of these you can say attention blocks. I'll discuss the combinations as well in the upcoming slides. The discriminator is basically VGG style. So here again the output generated by the generator is being passed along with the ground truth. So it basically distinguishes either it's real or fake. So here are some studies, like I use different combinations of those attention blocks. Like in the modified attention module, you can see I used channel attention block only, modified channel attention block only, a combination of CAB and spatial attention block, a combination of again MCAB and spatial attention block, etc. And the last one is basically I even experimented with the generator part where I used a GLU based VGG style discriminator. So these are some of the images. Like you can see this red block is modified attention block. So here I used CAB only, then I used CAB plus SAB, MCAB only, MCAB plus SAB, and etc. There were some other combinations as well. So evaluation metrics used for testing my results were some of the metrics which are highlighted as light blue are you can say peak signal to PSNR, SSIM, MSSIM, FSIM, and the other ones are SRSM, B-risk score, and FID. I'll come to this like why did I distinguish between the colors. Basically, some are distortion based metrics, like they compute the distortion in the images. Some are perception based metrics, the dark blue ones, the last three. So they perceive how the how humans perceive those images. So they define the quality of the visual image, basically. So basically this is the baseline model which we used, that is the ESR GAN, and this is the best model from all our combinations. So you can see our model basically give better results compared to ESR GAN in almost all the metrics. The first 5 are better if they have higher value, and the last 2 are better if they have lower value. So only I think in this one the B-risk score is slightly higher than the baseline model. However, our other variants have better B-risk scores than the ESR GAN. Otherwise, our best model has better metrics in all of the metric scores. Here are some qualitative results. You can see this was the lower resolution image. I have cropped the area. Basically, it is a 160 cross 160 image. So the ESR GAN has this kind of results when it performed the upscaling to 6 times. This is our best model, which basically upscaled it to 6 times, and you can see the images are defined, and these are the results of other variants as well. And this is the ground truth image basically in the end, which is our target image or we have to achieve. So discussing the results, the proposed RWSR GAN C variant, which basically uses channel attention block only, outperforms the state-of-the-art ESR GAN in almost all the metrics. And it basically retains the structural details and the overall contrast quite better compared to its variants. So this is the reason why we selected it as the best model. Other models, you can see that the channel attention block only with no modifications beats ESR GAN in all the metrics as well, but the visual results weren't that better compared to our best performing selected model. And similarly, the channel attention block plus SAB model also resolves this checkerboard effect. Like you can see here, it was this model without any modifications in the channel attention block has some checkerboard effect, like the circle image is appearing boxier. So adding spatial attention to it does resolve this effect, but the scores metric scores became a bit worse. Similarly, there are other variants. This one is the one where I basically modified the discriminator as well, but its results were a bit greenish. Like you can see here, although it's a bit cropped, but there was a greenish overlay over all the images. But still, it performs quite well in the metrics. So you can say that it can be used if the color contrast issues are taken care of. And the other variants also provided a smooth image compared to, but they weren't as good as the best performing metric. The important thing here is that we cannot rely only on the quantitative results. Like you can see in the table, there were some models, or you can say some variants which had better score even from compared to our best performing model, but like in the PSNR, SSIM scores, MSSIM values, but they do not correlate with perception based metrics. These are the metrics which I highlighted with light blue. So basically the visual images are not that well, so we have to incorporate the qualitative results as well. So concluding this presentation, well, basically this research utilized a real world data, that is world shred data, and we proposed a data preprocessing pipeline to enhance its visibility, and then we proposed a novel architecture, RWSR GAN, which outperforms the existing ESR GAN, and it leverages the attention networks like channel attention block, modified attention block, etc. And this model with modified channel attention block serves as the best, as it provides crisp and color accurate output, and it also overcomes the noise and checkerboards effect. And for future works, there are some other real-world data sets like MUS2, etc., which have a higher spatial resolution in the HR image, so they can offer a higher scale factor. And even we can utilize data sets from Pakistan, since Sentinel-2 and Spot 6-7 are available in our country for our country as well. So that's all from my side. Here are the references, and that's all. If you have any questions, you may ask. Thank you.
Thank you, Osama Shami. Anyone has a question? Do we have a question from the audience online? Okay, thank you so much.
Thank you.
Now we will have another presentation with the title of Improving Orthodontic Diagnosis Multi-Scale Feature Learning for Automatic Self-Metric Land Detection with Heat Map Regression. And the name of the author is Ms. Riha Khan.
Thank you very much. I welcome all the researchers, medical and AI practitioners to this session. And I'm really grateful to the conference chair for providing us the opportunity to present our research that we are carrying out at our research lab. I also welcome our online participants. In this particular presentation, I'll go through all our participants the research in which we just enhanced cephalometric landmark detection using multi-scale feature learning and heat map regression. Myself, Mohammad Anwar Khalid, and this particular research study is co-supervised by me. Reha Khan is the student that carried out this research, and I'm here to present on behalf of her. So first, let's establish some of the grounds that what cephalometric landmark detection, and before moving into the depth of landmark detection, first establish what cephalometric analysis is. Basically, cephalometric analysis is a tool that the orthodontists or the medical practitioners use to assess the deformities in the human skull, and based on that, they plan for the orthodontic and dentic surgeries. The process starts by identifying some key positions, key landmark locations. That's a point which you can assume as a 2D coordinate system having X and Y coordinates. So what they do is, if you can see on your right side, there is a cephalogram, a 2D X-ray image. And and on that cephalogram, they used to identify some key locations on various locations of the human jaw and human skull, and that is referred as anatomical landmark or specifically cephalometric landmark. So once the landmarks are identified, they used to connect those landmarks, and the lines joining those landmarks intersect at some point and make some angles. And that angles and the value of that angle represents how much the outer jaw or the lower jaw is out of the normal location. So based on that, they plan for their surgery. And since this is what they used to do in their day-to-day routines, this particular task is not as much easy as it perceived. So for example, if they have to do it manually, I observed them manually doing this. An expert orthodontist needs almost 30 to 35 minutes to trace one cephalogram. And most of that, if a dentist or if a human is going to do that, definitely they have inter and intra-observer variabilities as well. So in order to overcome the time consumption and the variability issues, we need an automated system to be there, which is given with an X-ray image and automatically detect the landmarks. And if the landmarks are identified, definitely joining them with lines and assessing the angles is not a big issue. And with this automated system, not only we are going to overcome the time consumption issue, but yes, if a computer is going to do, there is no variability as an automated system is going to do that. But there are some challenges. For example, a human skull is actually a 3D object. But when it is to be mapped over a 2D X-ray image, a lot of information just vanished or wiped out. The second challenge is the data scarcity, because it's a medical domain and we have some copyright and some patient consents, so we cannot have that much amount of data to train an automated system and have a precise landmark detection systems. So in 2015, there is a group who came up with a data set which facilitate the development of the automated systems, and the data set is proposed in a top-notch conference in biomedical imaging. The data set comprises of 400 cephalograms and acquired from a single imaging device with a single resolution, and the orthodontists or the labelers annotated each image with 19 different landmarks. So each image, that is 400 cephalograms, are annotated with 19 landmarks. Based on that data set, there is a complete revolution in this field in order to propose some automated systems. So if we can just conclude the literature review, we found two school of thoughts. One is the coordinate regression. Okay, we have an automated system, give an X-ray image, the automated system has to just predict the coordinates, X and Y coordinates. The second school of thought is proceed or formulate the problem into a heat map regression, which I will be explaining in the later slides. There are some other approaches in which they use a single CNN architecture, multiple two-stage cascaded CNN architectures. Once we have VN transformers, so transformers are employed, and now the literature is also exploring the fabric of graphical convolutional neural networks, GCNs as well. But since the data set is proposed in 2015 and the images are required from a single imaging device with a single resolution, the proposed architectures that are proposed over this data set has a biasness towards that resolution. There is no diversity in the data set. Moreover, since 400 images are there, not all the images are going to be provided to the model for training. Only 150 images are in the training set. So having that small amount of images, even we are applying augmentation techniques, since we have not generalization aspects in the proposed architectures. So not only we need some enhanced, proposed, precise and accurate landmark detection system, we also need some more and state-of-the-art benchmark data sets which has the diversity. And here our research group comes up with a new state-of-the-art data set referred to as arrays. We proposed this data set in 2013 in the same conference the previous benchmark was proposed. We also organized a challenge over this data set in which 29 different research teams participated and proposed their architectures and automated systems using that data set. The data set comprises of 1,000 cephalograms acquired from 7 different imaging devices with different resolutions. We annotated the images with 29 landmarks, and the first time we are having a data set in which we have soft tissue landmarks inculcated as well. The data set is not only annotated with the landmarks, but the data set is also annotated with CVM stage classification, make our data set to be the first benchmark in terms of classifying the CVM stage as well. So with the data set in hand, we also came up with a baseline architecture as well, in which we used a CNN model. You can see there are two parts in our CNN model. The first part is referred to as a backbone feature extractor. This backbone can be referred to as any proposed state-of-the-art CNN model. You can just, the proposed architecture has the flexibility to go in, like, just have another another backbone, just fit it, and the architecture will start predicting the landmarks. So the feature extract in the backbone feature extractor, we extract local geometrical features and global cephalometric features as well. But since you go through the backbone, from the start of the initial layers of the architecture, you have local features, local cephalometric features, geometrical features. But as you go through the backbone, you are making the features generalized and more generic. So predicting landmarks at the end, giving the features from the end of the backbone is not an accurate approach. So what we do is we come up with a fusion approach or fusion block as well, in which we took global features and the local features, we fused them and then used that high resolution features to predict the landmarks. We also use a technique that is referred to as heat map regression, and what we observed is we also have experiments with coordinate regression, but we also approached the problem with heat map regression, and we found that heat map regression is a precise one in terms of predicting the landmarks. Now what heat map regression is, as I mentioned, coordinate regression is given an automated system an X-ray image, and the automated system needs to just predict the X coordinate and the Y coordinate of a particular landmark. But it comes totally different when it comes to the heat map regression. In heat map regression, you can see there is a X-ray image and a landmark represented as a red spot, and the equivalent image with the same resolution, same height and width, you can see a blob at the same location. So you can view in a 3D, you can view it like a Gaussian distribution, having peak at the exact location where the orthodontist marked that landmark, and the standard deviation of that distribution is kept 10 pixels because of the clinically accepted range is of 20 pixels. So we just kept it in 10 pixels and make a Gaussian distributions. Based on that, we applied various segmentation models that I will discuss later on, and these are the results that our model acquired on the RDS data set. On the validation, we acquired 2.198 millimeters of the landmark detection error, and on test we have 1.942 millimeters of the mean radial error, with the success detection rate of 91.38%. That means 91.38% of the landmarks are detected in 4 millimeters, which is quite good. These are some qualitative results. As you can see, the image right on the left side is, you can see some red dots, that are the ground truth, some blue dots that are predicted by our model, and we also have some grad cams, like on the upside images shows where the architecture is actually looking, or the regions the architecture is paying attention while predicting the landmarks. As you go along, we have the image at second level, we have 1.46 mean radial error, and the image with 3.1 feel like a very large mean radial error is also shown here. So based on our abletion studies that we did on the segmentation models, the coordinate regression models, we found that heat map regression is more precise than coordinate regression, with a mean radial error that we achieve with 1.942 with heat map regressor and 3.5 with coordinate regression. The models that we use to test is multi-scale CNN, as proposed and shown in the previous slides. We also use some state-of-the-art segmentation models like PSPNet, UNet. We experimented around and we found that our multi-scale fusion-based CNN architecture outperforms the state-of-the-art proposed segmentation models. So at the conclusion, I conclude my research on these bullet points. The first one is multi-scale CNN, in which we just fuse the local geometric features with global cephalometric features that outperforms the state-of-the-art segmentation models. Heat map regression is found to be the best approach, or the more precise approach in terms of, or in comparison of coordinate regression. And in terms of performance, we achieved 1.942 millimeters of mean radial error, which is in the clinically accepted range. So that's all from my side. If you have any questions, the floor is open.
Thank you very much for your presentation. Any questions from the audience or online participants?
So you mentioned that you have incorporated features from different layers of the model, and these features dimensions get changed as they are progressing through the model, and then you have to fuse them, like 3 to 4 different stages, fuse them together. So how do you fuse these features if they have different dimensions?
Okay, let me go to the exact slide. Oh, yes. So if you can see, when we are fusing features from the later layer to the features from the slightly earlier layers, we are applying some convolutional layers in which we are going to not only reduce the channel dimensions, the depth of the features, or you can say the spatial dimensionalities of the features, but also the spatial resolutions to keep intact while we are fusing it. So based on that, the fusion, we not only actually fuse the features, but we also get or keep moving in terms of the encoder-decoder architecture. So we keep on increasing the spatial dimensions, but in the meanwhile, we also fusing the features as well. Hopes that's the answer of the question.
Any more questions from the audience?
Thank you. It's really interesting, your research work. I am also working on cardiac imaging and work also with PJH Hospital, Malaysia. So kindly please, can you tell us, as you mentioned that you are using the segmentation model, which segmentation model are you use for this research? Region-based, active contours, level set, variationals, yeah, active contours, yeah, shape-based approach, which model you used? For my knowledge just.
Okay. Okay.
Thank you.
Sir, in computer vision, there are some proposed state-of-the-art segmentation models. Basically, the core architecture remains intact. They just use or play around the layers, and that core architecture is encoder and decoder architecture. So we also experimented our results with those like UNet, PSPNet, SegNet, and some variations of UNet as well, like UNet plus, UNet plus plus, UNet X, some variations in UNet as well. But we found that all the conventional segmentation models with encoder-decoder architecture are not like precise such that they can make the landmark predictions in the clinically accepted range. Then we, as I shown the GradCams, when we utilizing the GradCams, we know that the model is just struggling by identifying the key locations because of the very much precise range in which the model has to predict or identify the landmarks. Having that GradCams, we just came to know that we need to fuse because we are giving the most general features to the model, and based on that the model is going to predict. We need to inculcate or fuse some local features, and what our architecture that we proposed is the an encoder-decoder architecture, of course, but with a fusion block as well, so that the fused features can help the model to detect the landmarks in the accepted range. So it's intact, the core segmentation models that we usually employ in computer vision.
Okay, I have a few quick questions.
Okay.
One is like, are these landmarks standardized? I mean, we all in computer vision have been working on face recognition, facial analysis. So the first thing is we identify the landmark on the face are points on the eyebrows, the eyes, the nose, the mouth. So this is the problem of orthodontic diagnosis. So
Yes.
are these landmarks standardized in your domain?
Okay.
And my second question is, what organizations are you collaborating with? And the third one is like, is this data set still open for research?
Okay. Answering the very first question, are these landmarks are standardized? As I mentioned that in terms of the facial landmarks, so if a landmark is there on the tip of the nose, the model has the like flexibility to put it either on the tip or he can go a bit slightly up and down. But here the model has only 20 pixels range. If the model is not going to predict that in the 20 pixel radius, that prediction is not be considered as a success prediction, number one. So yes, the landmarks are standardized. They have a pretty much precise range in which they are need to be identified, otherwise they are not considered as a good prediction. The second question is, I guess, which organization we are collaborating with. So the data set is actually meticulously annotated in collaboration with the RIFA International Dental Hospital with a team of 6 expert orthodontists, in which their experience lie from 10 to 15 years, the practical experience. So we have 2 phases, in which the first one we labeled the data set. In phase 2, we reviewed the data set. The labelers reviewers reviewed the labelers labeling. The third question is the data set still open to the public? Yes, the data set is open to the research community. We have a platform in which you can apply with a consent that you will be using the data set to for solely the research, and the data set will be given to you.
Sorry for again asking a question, but I get interest in your subject, that's why. Actually, we are not a medical doctor, we are a computer scientist. So basically the data come from the experts. So what is the mean error, what is the error between your results and the expert results? You found there is any a big gap for the future's problem for the researcher? If you would like to share with us, what is the main errors come between you and the expert results?
Okay. Actually, the mean inter-observer variability of our reviewers and the labelers, if we take the mean, that is 1.49 millimeters, and right now with this baseline, of course, we have a 1.92 millimeters of the radial error. That means the automated system is not making a very good prediction as a human did. But if you consider this in terms of human, the inter-observer variabilities vary among the landmarks. So with 1.49 millimeters of the inter-observer variability, the orthodontists are found to be way weak in predicting some of the landmarks because of the identification region of that landmarks. But our automated system did quite well in that location. So this is a trade-off. Since the data set is public, we welcome the research community to come up with their solutions, and if they can reduce the error from the human error, so that's the win situation for artificial intelligence.
Okay,
of course.
thank you, Mr. Anwar Khalid, for giving us the insight about the orthodontic diagnosis. Also thankful for the research contributions in the areas of medical healthcare. Due to the shortage of time, it is requested to please complete your presentation within 10 minutes. Now I would like to invite our next presenter, Mr. Syed Hussain, for the topic of a novel prediction model for Alzheimer's classification using deep learning. Okay, it's requested Ms. Shehnan Madhusanka. Is she online? Can we have an online presentation for the time being?
Yes, I'm here.
Okay, kindly share your presentation. Thank you.
Good afternoon all. I am Shehan Madhusakar from Faculty of Engineering, University of Peradeniya, Sri Lanka. And our research topic is optimizing dental education, systematic interaction design and evaluation of the virtual patient simulator. First, let's focus on why simulators become popular in dental education and what are the limitations in dental education and traditional teaching method. One limitation is traditional teaching method is highly tutor dependent, which means that each step student follows, they need a significant tutor guidance and instructions. But with the limitations of resources and time, this could be challenging most of the time. Another limitation is dental learning need the direct patient interaction, and this could raise some ethical concerns, such as the patient safety. Because when students interact with real patients, mistakes can happen from them, and that can cause some troublesome situations. And the scenario limitation is another problem that we can identify through traditional teaching methods. Because with the traditional teaching method, student may not get the exposure to a wide range of clinical patient scenarios, especially with the complex and rare cases. As a solution, virtual patient simulators have become popular among dental education, but it has some limitations as well. One potential problem is the limitation of available patient cases within a simulator. This restricts the scope of the student learning and reduces the exposure to a wide range of clinical scenarios. Lack of feedback mechanism and the need of high technology are common limitations of available simulators. As a solution for this, we introduce a novel tutoring type virtual patient simulator. This provides a web-based simulation environment eliminating the need of high technology and power where users can access the simulator through a web browser. The simulator is designed under four main phases, which are history taking, examination and investigation, diagnosis, and feedback stage. Also, the simulator contains with an interactive 3D model via a 2D web interface with the features of extraoral and extraoral and intraoral view, dental room, and instrument selection. More importantly, the simulator features an interactive design incorporating HCI methodologies, which we have evaluated with usability testings. This is the system architecture diagram of the virtual patient simulator. The front end was developed using React, and Unity game engine is used to model the 3D view. Then the backend is developed with Node.js, Express.js, and Firestore database is used for data storing, and the system is hosted in Firebase platform. This diagram indicates the interaction design of the VPS interfaces. Users can start with logging to the system, and they can select a patient case. Next stage is to complete the patient history taking, and once completed that, user will directed to the patient examination by using virtual 3D patient. For that, the necessary instructions are provided within the system. User can engage with activities such as extraoral examination, intraoral examination, dental chart marking, dental tooth drawing, etc. Based on the patient case they have selected. At the same time, they can answer the questions popping up in the left side of the interface, and finally a feedback will display explaining the user activity. Now let's move on to the findings and results. We have conducted an HCI evaluation to assess the usability, user satisfaction, and navigational ease of the system, and to identify the key areas for further improvements. To do this evaluation, we assessed 10 dental students, and initially an informed consent was taken from each participant for their voluntary participation. Then the participant fill out the pre-questionnaire, then they interacted with the simulator activity, and they completed the simulator activity by filling out the post-questionnaire form. During this time, the researcher recorded the time taken by each student to complete the simulator activity, and noted down any key areas where participants experience difficulties. Once students completed the simulator activity, we have evaluated their feedback using 5 targeted questions with a 5-point Likert scale. These graphs shows the distribution of the responses we have obtained for each question separately. We can see almost all the ratings are biased for above good range, but we can see there are some areas that needs to be improved more. In this graph, we can see the average values of ratings given by participants for post-questioning. Each bar represents a different aspect of user experience with our virtual patient simulator, such as navigational ease of simulator's layout, clarity of instructions, quality of graphics, user-friendliness of the controls, and overall user-friendliness of the interfaces. We can see the average values are about 3 out of 5 ratings. With the smaller sample size, we can say there are areas that needs to be improved it, but we can observe that overall user satisfaction and user experience is a positive one. And we conducted an ANOVA test to check whether any of the factors such as students' proficiency level with computers, their gender, their academic semester, or their web navigation familiarity have a significant difference with the time taken by students to complete the simulator activity. Based on the data we observed via pre-questionnaire, we calculated the p-value for the completion time versus each of these factors, and we obtained all the p-values greater than the threshold value, which is 0.05. With that, we can say there is no any significant difference in the time taken on any of these factors. And lastly, for the future directions of this virtual patient simulator, our goal is to integrate a haptic device for the 3D model for better experience with tactile feedback, and expand the patient case libraries with complex and rare cases. Also, another future direction is to enable custom patient case creation within the system, and a potential enhancement can be integrating a virtual reality technology to get a immersive clinical experience. So this is the end of our presentation. Thank you.
Thank you, Mr. Madhushankar, for presentation and research contribution in the field of virtual patient simulation. Do we have any questions from the audience? Okay, thank you so much. Our next presentation is a novel prediction model for Alzheimer's classification using deep learning. And the presenter is Mr. Sayyid Hussain.
So, well, my name is Amjad Khan. I am presenting the loan predictions model for Alzheimer classification using deep learning. I'm from Basin University Islamabad campus as an associate head of the Department of Computer Sciences. So this research, my two of students, one is Syed Ahmed and the another one is Bilal, under the supervision is Dr. Sadaf Tanveer and my Dr. Amjad Khan. So the basic theme of this research is Alzheimer's. What is Alzheimer's? Before to start with the detection process, Alzheimer is basically the disorder, the brain disorders disease, where mostly the patients losing of talks and losing of dates, losing of dates and not remember anything. So the symptom of Alzheimer is memory problem is basically. So what is the role of machine learning and deep learning in these research areas? The role of machine learning is to diagnose in early stages the Alzheimer disease and to predict the level of Alzheimer diseases. That is the data set images. Samples are taken from the Alzheimer data sets, taken from the Google Gaggles. The one example of sample is a mild demented and the another one is moderated demented and the third one is very mild demented samples of the images. The model is for the proposed model we use the CNN models for this. There are two types of classification. One is the pathological classification and the another one is unpathological classification. The non-pathological classification is the normal images classifications and the abnormals shown in demented, very mild and mild demented. The models experimentals is used in the performance measurements and the another one is the confusion metric use. So in the performance measurement we got 96.4 accuracy rate of the as compared with the previous studies. And then we use the precision and the F1 score which will be show in the result sections. The confusion metrics we use to observe for the expected and the observed values of the demented, the very mild and non-demented patients data. That one is some visual representation which we got the data from the data set, the Alzheimer data sets. The example of the visual representation is here. And that is the resulted images which is we classified by using the models. That is a normal case also and the pathological cases also. the results of the expected, we use the kernel size also. The performance evaluations, we use the kernel size 3 by 3, 5 by 5, and 7 by 7, which is a very common matrices. And a filter size is 32 used for the 3 by 3 and 5 by 5 and 7 by 7 matrix. So the recall value is very real and good values is 0.9877, and for the other patient also, the experiment, three-time experiment were conducted for different patients, which we have 2,000 and 23,000 and 100 images we have in the data sets. So these are just samples results of the some of the patients. The precision value we have, the accuracy is we got 95, 95 and 95, but the actual accuracy between when we conducted is 96.4 point, got it in this research. We have the performance evaluation of proposed CNN model, which use for the number of filters we use. Different filters are used: 8, 16, 64, 48 and 64, 96 bit filter we use. Before we use only 32 bits filters. Now in this case we use the 8, 16, 64, 48, 64 and 96 filters, and the kernel size also is different in these cases. We use the patterns of the kernel 3 by 3, 5 by 5, 7 by 7, different patterns for the different experiments. Thank you very much. For the shortage of time, we just presented the data, special data. So any question, please. This is just a pilot study for the Alzheimer's patients. Alzheimer is basically very different. So the classifications just in the early stages, if the doctor did know about the patient symptom, then they can be reach for the solutions. So the study is just for the classifications, classification mode, not the detection base, to classify the data in pathological and non-pathological cases. Any question, please? No. No, we don't have the hospital data. This is just a pilot-based studies using the Alzheimer's data sets, which have 23,000 images. Whereas 16,000 is training base and other is testing base. Yes.
Any question?
Ji.
Hello, sir. So I have just a small question. Like you showed the results, so these are quite good. But are there any baseline models which you targeted, like you have to achieve above certain threshold? And also in medical domain, like is there any specific threshold, like you have to cross 90%
The
or
threshold
95?
is 0.2. We set it for the images, and along with the threshold, we use the histogram equalization in a pre-processing. That is 0.01.
All right.
We set it for the image.
I mean, there is any accuracy threshold as well, like you have to beat the minimum accuracy, say 90%, or you have to be above 95%?
No, there is no accuracy threshold. There is the threshold is just like if we have the intensities value from 0.1 to 0.9. So actually the from 0.5 to 0.7 is the threshold value, which is identified from the American Health Association, especially for the Alzheimer disease, which find out the Alzheimer classes. The three classes: one is demented, the another one is very demented, and the another one non-demented cases. So they differentiate. If 0.5 is set on the data, then it will be called the demented. 0.6 is non-demented, and the 0.7 will be set on the very demented data.
Right. Thank you.
Thank you. Please, another question.
Oh, okay, thank you everyone. I would like to thank all the participants of this session. And especially I would like to thank all the authors of the paper who have presented their excellent work. In the end, I would invite you all to talk and find your future collaborator in the break session. So thank you very much.
Thank you.
Okay, we have Dr. Jamil, and he is going to distribute the certificates to the authors. Thank you, sir.
जी फर्स्ट मुसलमान साहब सामा शामी Mr. Sama Sami. अच्छा यही जी नेक्स्ट वन कौन है रिया खान आई थिंक शी वाज ऑनलाइन Sir Anwar, can you please join us? Anwar Amjad Saab was the former DGIT of HEC. Actually, okay. Okay, we have shields for the chair also. Ji Numan Saab, please. Ihtisham Saab, please. Ihtisham Saab is the chair of this conference also. He's worked very diligently to make this conference successful. Special thanks to him. Special thanks to him. Thank you, Dr. Jamil. Thank you, Narvasa. Thank you very much. For now, the lunch is ready. I think it's also served, so please join us in the lunch.